This project is inspired by Robocop football. The goal of the robot is to find a ball on the 2x2 meters field and to score as many goals to the goal of the given color as possible, whilst avoiding to all obstacles on the field. However, the robot has to comply with several rules. It has to fit into a cylinder with the diameter of 180 mm and height of 225 mm. It cannot capture the ball more than by 20% of ball's volume, and it has to be mainly black. To successfully complete this project, 4 subsystems have to be developed: navigation, vision, drive, and kicker and dribble subsystems. The kicker and dribble subsystem wasn't completed due to the leaving of the 4th team member. Now let us present you each of these subsystems. My name is Jakub Slama and I'm responsible for the image processing. Understanding the surrounding world is a key factor to fulfillment of this task. Therefore, the robot is equipped with RGB camera to be able to understand the world. We are looking for objects of 5 different types: blue and yellow goals, obstacles, walls, and obviously the ball. All the objects are segmented from the camera image based on color thresholding in HSV color space and morphological operations. Here in the example recording from the robot, we can see the output mask for each object type as well as the final labeled image. Although we can segment desired objects, we also need to determine the bearing and distance to them so navigation can do a proper planning. To do so, we determine the visual size of these objects based on the data in mask, for example, by approximating the ball as a circle or obstacles as rectangles. Afterwards, we can determine the bearing and distance based on measured visual dimensions and no real dimensions of these objects. This information is provided to navigation subsystem to allow a planning of movements and action of robot to score goals.
Hi everyone, I'm Michael Dowd and I'll talk to you today about how our soccer players think during the game by imagining myself one of them. As a starter, my main objective is to get the ball and score the goal. Quite easy, quite simple, but what if I really can't find the ball? Well, I'm just gonna have to look to my left 45 degrees, and if I still can't find it, I'll just loop around myself once. And if I still can't find the ball, then I'll just look for a dead end, or in this case it's gonna be the goal, and go the other way around until I find the ball. Alright, so I'm left in a situation where I can't either find the ball or the goal, so my only option left is look for the clearest and safest path, and just look for the ball there, and if you can find it, cool, just score the goal. Alright, so in this scenario, we can see the ball, but we also see there's an obstacle on the way preventing us going straight to the ball. And from the rules, we can't really touch this obstacle, so our only option is to use a strategy we call reactive local planning. Pretty much what it means is, don't worry about what you saw in the past, just focus on what you currently see and decide the best decision to make for the future. Well, in this case, our best decision is find the angle on the step that can make us a step closer to the destination while avoiding all these obstacles on the way.
A complete robot product requires a drive system which can achieve a well chassis design and cover design which is satisfied with the F180 rules, a functional PCB board design, and the complete product can also speed up and maintain particular speed, able to rotate and turning. Have a good software communication design that able to control robot by commands, can be also easy to integrate with other subsystems. For the chassis design and cover design, the diameter of the robot is 130 mm and 120 mm high. Design an indentation at the front of the robot for dribbler and kicker. Reserve 2 holes at each side of the indentation for dribbler mounting. At the drive system, using 2 motors at each side to achieve differential kinematics. Control the motors by PWM, achieve speed change, turning, and rotation. The PCB board on the robot consists of 2 motor driver and voltage regulator module pin. The internal motor driver can apply PWM and direction control for 2 motors. The voltage regulator can supply power for Raspberry Pi. It can step down the voltage from the battery. At the end of the software design, connect with same hotspot or Wi-Fi using VNC to control the Pi by computer. When running the motor control Python script, it is easy to control the motors by typing commands.